Hola a todos, nuevamente aquí en la JConf Perú 2022. Bienvenidos. Vamos a iniciar la charla aquí con Chris Engelbert. Eh, Chris es un developer de corazón, con muy fuertes vínculos para la comunidad o el mundo de open source. Es also un speaker de muchas conferencias. Le encanta compartir sus experiencias, sus ideas, especialmente en las áreas de arquitecturas de sistemas escalables, de tecnologías en backend y todo lo referente a lenguajes de programación. Así que vamos a iniciar con su charla Postgres, the time series database you actually want. So, Chris, welcome, and again, thank you for your presence.
Thank you for having me. Great pleasure. Never been to Peru, so looking forward to maybe coming over next year. The only country so far that I managed to do was Brazil. So yeah, thank you very much for having me. Today we're going to talk about a little bit about Postgres. One of my guilty pleasures. I know I'm coming from the Java background, and that's what all of people know me for. But Postgres is a thing that I'm really in love with for a long time. Whenever somebody asks, like, what would be your database of choice, there's always a good chance that Postgres is like the first answer. And only if you figure out that Postgres is not the answer you're looking for, at least in terms of relational databases, then you probably want to look for something else. But today we actually gonna look for a little bit something which is different from the typical relational database stuff in Postgres. So we're looking at time series databases or time series data in general, and how we can store that in Postgres. And with that, let's just quickly go. This is me. I'm Chris. I'm actually Christoph, but for a lot of countries that does not really fly. So Chris is just fine for me. I'm a developer advocate at Timescale DB. Yes, we are a time series database. We are built on top of Postgres, which is great. As I told you, Postgres is one of my guilty pleasures. I've been with a lot of companies in the past. One of the most famous ones is probably Ubisoft, but also Hazelcast. That's probably where a lot of people in the Java community know me from. And then I've been at Instana. We were an observability tool, trying to help people understanding how the systems work and all the kind of good stuff. If you have a microservice system running, there's a good chance you really, really want to look at that. And for the last 2-3 years, I've been with my own startup, Cleverbit, and we were trying to figure out, or not figure out, we were trying to help making the animal husbandry, like animal farming industry better, getting better health and better welfare for the animals. So, well, I said we tried. It didn't work out. No hard feelings here. So now I'm with Timescale DB. We use Timescale at Cleverbit. That's how I got into all of the time series and timescale technology. And in general, my interests are everything developer relations and everything performance engineering. I'm coming from a strong performance engineering background. I love everything about benchmarks. I love how one-sided they are. I love how wrong they normally are. And I love how people still claim that C++ is much faster than Java, even though this is just bullshit, right? But my favorite fairy tale is AMD versus Intel versus NVIDIA, and who's faster than who. And if anyone believes any of those is actually faster, except for Intel, let's leave them out of the game. But NVIDIA and AMD, they don't really do themselves anyway. If you want to follow me, Twitter, Mastodon just being added recently. Happy to answer any question, but I'll also be in the chat for minutes after the talk. So before we start, we need to talk a little bit about, or think about, what is a time series. And I picked a couple of examples. I brought them with me, and let's just try to figure out what a time series in itself means. And believe me, there is much more time series data and much more time series data models in the world than you might believe, because basically everything we do these days are actually time series. And the easiest thing to start with is anything financial transaction, right? Every time you do a financial transaction, you have something related with time and data. Most of the time it is something like you pay for something and somebody wants to get paid. But it relates by time, right? If your account is empty before you want to pay something, that is different than it is empty afterwards, right? So financial transactions like the most obvious kind of thing, but anything stock market, and we're still staying in the financial industry, right? And the stock market is the same thing. You have data which relates to time. They changes over time, or the stocks change over time. And yes, that's my favorite example. That is exactly the Bitcoin stock price over the last, I think, 12 months. Beautiful, right? It's a perfect distinction between two colors, green and red. And no, it did not come up yet. This is the Internet of Things measurements. That is the system or the hardware that we created at Cleverbit. So everything IoT metrics, doesn't matter if it's temperature data, if it is like position information, like tracking a car or cargo or anything like that. Anything Internet of Things, or especially the industrial Internet of Things, like the IoT, that is complete time series data. And it makes perfect sense if you think that all of those measurements only make sense if you look at them in the relation of time. I said I've been with Instana, so anything observability metrics, right? Observability metrics may be anything from CPU metrics over memory consumption, service crashes, service restarts, anything like that. And it only makes sense if you think of it in a chain of events that happen over time, that have a relation to time. Same for service traces. So trace is something you call a service, and that service calls another one, and maybe another one in between. And all of those information, they need to be tracked over time to understand, like, how is the request, how is the user behavior, or how is the answer for a user request happening in the system? How is it calculated? Where is time being spent? Stuff like that. How are services being related to each other? How do they communicate with each other? Is there actually communication between services? All that kind of stuff. One of my favorite examples, and something which we don't often think about because that is something which is really internal to companies, is any kind of user behavior tracking. So Netflix is super open about that, and I really love that. They try to sell you more, obviously, right? They try to upsell their streaming service, their subscription, but they also try to keep you longer on the system. And the way they do that is they try to understand what is it that this specific user likes to watch, and how can we make him watch more, but also how do we make sure that we feed him the right information, the stuff that he actually likes. And as I said, Netflix is super open about that. There is an incredible YouTube talk, or there's an incredible conference talk on YouTube about it. That is one of the screenshots from it. It's absolutely worthwhile watching. If you're interested, I'm happy to share the link afterwards. I just need to find it. Unfortunately, I didn't drop it on the slides, which is a stupid mistake from my side, but I'll do it for the next conference. And one of the more like funny examples is the actual Marvel timeline, because there's so many movies and so many stuff on Marvel, and series and episodes and stuff like that. You actually have to put them into a timeline and plot it to keep track of all how the world changes, how the stuff happens, what the order is to actually watch all of that, to make sense of the world building they're trying to do in the movies and the series, and let's face it, in the reboots as well. So anyway, that means time-related data or time series data is anything that observes a specific subject changing over time. So it's a time-related observation of a subject. As I said, if we take a temperature measurement, how does the temperature measured by a specific sensor changes over time? So the subject would be the sensor, and our time-related observation would be the temperature changes. For stock, it would be the subject is the actual stock. We have the Bitcoin tracking or the Bitcoin market share or market value. And how does that change over time, right? So anything like that. Two examples how that would look in a relational database. I think it's obvious, right? We have something which is a time, we have a price, that is the actual observation, and we have a symbol which is the subject. Same for an IoT measurement. The measurement would be like what we look at over time. We have the device ID, which kind of is like the subject, right? It's a specific device. It may be a sensor if you have multiple sensors per device, stuff like that. You have the sensor value, which is the actual value that changes over time, and you may have additional information, and that's the beauty, right? We're in a relational database, so we can have additional metadata. In this case, maybe the location, because the location of a device may change, right? If you have like a tracker around the neck of a cow, the cow may move going inside the barn, walking around the field, and you want to know where the temperature was actually measured, stuff like that. It's a stupid example, but you get the idea, right? To understand the volume that you can see with time series, and we're often talking about stuff like big data, and a lot of people, they expect like 1,000, 10,000, 100,000, maybe a million measurements per day is actually big data. But if we look at the New York Stock Exchange, so that is what the NYSE means, they actually have 4.2 billion transactions on a single day, which is nuts, right? Just try to imagine this number, like 4.2 billion transactions on the stock exchange, and that is just New York, right? There is more than of them, and that's 162,000 per second. If you have that number of requests going in and you can handle it, you know you're doing everything right, right? But the interesting thing is the New York Stock Exchange has to keep all the records for 5 years. So that means, remember, we have 4.2 billion. I just love the number. 4.2 billion numbers, records per day, and we have to keep all of that for 5 years. That's a 5.4 trillion. I wouldn't even know how many zeros that is. 5.4 trillion data records that need to be available, that need to be queryable, and that need to be analyzed in some way. Or in the worst case, if somebody on the website asks you like, hey, please plot me like the stock price change for that specific stock for the last 5 years, you actually have to take all this data and try to render it. And that is where the insane thing comes in, right? Try to render 5.4 trillion data points. It's not going to happen. Anyway, so that is what time series in general is, and that's what the kind of like volume we're looking at when we're looking at time series. At Cleverbit, it was not as much. We've been in the millions per day, but still, right? We were a small company, and we expected it to grow, not to those numbers. We're not a stock exchange. We're not in high frequency trading, but certainly there is a couple of things that you really want to think about when you do that. So, with that, why would you consider Postgres for a time series data set anyways, right? I mean, there are specific time series databases like Influx, QuestDB, ClickHouse, all kind of stuff. For us, it was simple. I knew I wanted to use Postgres, and I knew I needed a time series database for all the IoT metrics. So I shopped around a little bit, and I found TimescaleDB. And it was interesting, right? TimescaleDB, a plugin, an extension based on or built on top of Postgres. That means I can use the same database that I wanted to use for all the other stuff. I didn't really think of specific use cases that made it happen that we eventually split the databases. But for the first 5, I was like, cool, I can use the technology that I use, that I already use, that I love, and that I know. And using a technology that you know and understand how to operate is much easier than just trying to come up with something new. So why Postgres? Well, Postgres rocks. That's it. That's how simple it is, right? And if I didn't convince you yet, I'm pretty sure Postgres rocks. Just try to change my mind, right? But to be a little bit more serious here, The reasons are simple. Postgres has an extremely established ecosystem. I mean, we're in the Java community, right? We love the Java ecosystem for what it is, for how stable it is, how far developed it is, established. We have everything that we need. If you need a library, there is a high chance there is one just around to being used. And that's the same thing for Postgres, right? If you look at Postgres, the Postgres ecosystem, there's probably the thing you want and you need is just around already. It is rock solid. It is around for years and years. I mean, let's face it, Postgres is the only open source enterprise database, or at least enterprise relational database. I would even say enterprise database. It's rock solid. The storage engine is rock solid. It is very unlikely to see an issue with the data storage that is not recoverable. There's a lot of tools around it for backups. There's a lot of tools for managing a multi-node cluster or a leader follower cluster. Read replicas are supported, hot standby is supported, all that good stuff, right? It's production proven. No thing about that, right? People are using it for years. They're happy. They have massive databases. It's not like a few million records. There's billions and trillions of records stored in Postgres, and it just works. And that's beauty. And I'm not the biggest SQL fan, and a good friend, Lucas Eder from Duke, he may say that because we had a lot of discussions in the past, but let's face it, SQL is an awesome language. You can do everything and even more with SQL, including all the weird stuff like recursive SQL queries. It's Turing complete. Do we want that? I don't know, but it works, right? And you don't have to learn a different language. Flux or whatever, PromQL, all those languages, they may be powerful, but the learning curve is pretty steep, right? And there's two important things, and that is basically what we talked about today. Postgres can be multi-model. It's actually multi-model by default because it supports JSON and stuff like that. So it's basically a document database already, and that out of the box. But it also supports all kinds of other stuff. There's extensions to support graph data. There is PostGIS, which is for anything geo informations, right? There is timescale, which gives you time series database. There is where it's CStore, which is a columnar store, and even timescale in itself has some kind of a column or columnar store when you compress data. So you can basically store everything in a single database, and the beauty is joins work. They literally just work, and you can join anything together. You could ask your graph extension for, hey, please find all companies of a specific region which you query, or a specific area which you figure out using PostGIS. And when you have all the buildings or stuff, you could say, hey, please give me all the indoor temperatures and all the outdoor temperatures. And then you could do some magic with that and trying to figure out some average values and stuff, right? It literally just works. And the most important thing, I guess, elephants are just awesome, right? I love elephants. So obviously Postgres is like a first choice. So, but we're talking not only about Postgres, but we're also talking about how to actually store time series data in Postgres, and why I think Postgres is the perfect data storage to do that. As I already said, it's a rock solid, it's an established storage engine. As long as you don't change that, everything is good. But to make stuff fast, and you probably know that from other databases like Oracle or a SQL Server, stuff like that, you need to start partitioning data, chunking data, sharding data, whatever you're going to call it. And Postgres has an old version of how to do, well, at that point in time, I would have called it sharding. It has a new version of partitioning. And in the last set, we're looking at how easy all of that can be if you use timescale, because we are exactly built for that use case. But there is no need to use timescale, and that's what I want to show you. You can do all of that if you want to go the extra mile. You're free to do that. So first of all, partitioning, sharding, chunking, whatever you're going to call it, it's always the same thing. Instead of having one massive table, we're talking about 10 terabytes here, for example, we're going to split it into multiple subtables that all are aggregated into this one thing. It all looks like the same thing, right? You query the root table, and you don't understand from querying, at least, that the data is chunked in or stored in multiple partitions, multiple chunks, as I said, whatever you're going to call it. In the past, we called those things charts, and we normally had number ranges or stuff, and we all knew number ranges are a pretty bad idea. Yeah. But okay, you remember we had 10 terabytes and we split it into 4 tables now, with 2.5 each. That is still pretty massive table, right? So what we want is like smaller tables. We want more of them. We want them smaller, and we want them partitioned in some way. A pretty good example or a pretty good number could be 1 gigabyte, 2 gigabytes. It all depends on how much RAM you actually have. And in terms of like how we can actually partition the data, at least in Postgres, you can have range partitions. These are the number ranges. They may work for certain things like customer IDs or stuff if all your customers are the same size, which is very unlikely, but it is what we had in the past. But ranges could also mean like time ranges, right? It could be like a month or a week or a day. You have list partitions. List partitions, basically every partition you assign numbers or customer ID specifically. So you have like 20 small customers, you can all assign them to the same list and the same partition. And you have like really large customers, so you may assign them to their own partition, or maybe just 2 of them inside of the same partition. And then you can do hash partitioning, which is basically the thing for anyone who ever used Hazelcast in the past. Hash partitioning means you're building a key. You're taking the fingerprint, the hash, the consistent hash of that key, whatever it is. And if you have 10 partitions, you use the modulo operator and say modulo 10, and then you get it assigned to one partition. With a large number of objects and basically the same size objects, and a high cardinality or a lot of different objects, hash partitioning is really good. There's this really good chance that statistically you get a really nice distribution. For a low number of objects, that is not really a thing. And why do we do that? There's a few really important things. So smaller tables. So in case you don't know, or if you have never looked at like an execution plan, which basically tells you how the database would execute your query, there's a couple of different things. And one of the, most of the time at least, worst things you can do is a sequential scan. A sequential scan means if I have like a table or a list of 10 items, it actually has to look at every single item in sequence. That's a sequential scan. Now imagine you have a 10 terabyte table with a trillion rows, and the database decides for whatever reason it has to do a sequential scan. Obviously, that's much worse than having a gigabyte table with only like, I don't know, like 10,000 rows, and it decides to have a sequential scan on those 10,000 rows. The likelihood of happening that with the large and the small table is not the same. But in general, smaller tables are much faster to scan, even for things like indexes, right? We have indexes per partition, which means if for some reason I understand that I don't need to look at certain partitions because they're out of a specific time range or something, I don't even need to look at their indexes. If I have just like one massive index, obviously I can't just extract data or say, okay, I don't need this, but I need that. And it's really hard. I still have to look at all the index. But smaller indexes are specifically interesting when you need a lot of updates, because updating a smaller index is much faster than a large one. Partition pruning is exactly what I meant earlier. If you have like 10 tables and you're looking at a month and you have monthly tables, you may only need like one or two tables to have all the month or looking all months back, right? And all the other 8 tables, they don't even need to be understood. We don't even need to look at those, which means we can prune them from the query. Pruning means there is some early exclusion ongoing and saying, hey, I see I have 10 partitions, but those 8 are completely out of the scope, so I don't even need to look at those. And then there is partition detach. At least that's the terminology that Postgres chose to use. Partitions are attached to a parent table or a root table, and you can detach them at any point in time. And detaching means that they're not part of this like root table anymore. Data is not queryable from the root table anymore. And that means you can detach a partition and basically immediately make data invisible. And then you can just delete or remove the actual partition table over time without the data being available. Anyway, so we're 25 minutes in. Time for a little bit of a demo, right? That's what we all waited for because we love demos. All right, so I hope you can still see my screen, which is great. And what I have here is a timescale cloud instance. Timescale is an extension for Postgres. You can use it on your local Postgres instance. You can use it on any Postgres self-hosted Postgres instance, but obviously Timescale has like Timescale Cloud as well. And it's super simple to use, right? You get a database for free for 30 days to test it out, but you get all the benefits and the toolkit, and the toolkit gives you additional functionality, which is great for anything time series analytics. So just a plain empty database, nothing fancy going on. So let's start with the like elephant in the room, right? The typical Postgres stuff, the stuff that we would normally do. We already know the database is empty, so that does not do anything. It's just to make sure that there's actually nothing happening or nothing around. And then we create a table called measurements. And you remember a measurement is, or at least in a time series, measurement is a timestamp and some kind of value. In this case, where we called it reading. So we create the table. And that does nothing else than generate a series of 3 months. So June 1st to August 31st. With an interval of 10 seconds. That was originally created, or that example was originally created for the JJAC CCC in Japan. Let's try. To be honest, I'm not sure if that is going to work. But let's try at least, and let's say we're adding 10-second values in the time zone of Peru, and we have some reading somewhere in between of 10 and 50. And let's execute that. No, Peru is not recognized. So right, let's leave Japan. If anyone knows the time zone in Postgres for Peru, feel free to drop it in the chat. Happy to do that. So we're gonna generate the demo data, and that is happening right now. Don't look at the numbers. The database is not warmed up. I just started the virtual machine, so it doesn't really matter. But what we see is we created roughly 800,000 rows, which is a good number of, right? So we quickly create an index on that. That should not take too long, and we're done. The interesting thing is when we now look at the execution plan. As I said, the execution plan is what you get when you ask a database like, hey, please explain me, right? Explain me how you would execute that, that specific query. And the query is, hey, just give me all the data from July 14th to July 16th. So we're just asking for 2 days in a time frame of 3 months, right? So I can ask the database, and the output is not too large. We see it's doing an index scan, right? We have an index on the timestamp. Glad we did that because it figured out, hey, cool, I can actually look at the timestamp and figure out what the heck is going on and where to find the information. And it says, well, we found 17,280 rows, and the interesting thing is it tells you what is the expectation before actually executing the query, and it tells you what was the result after executing the query. And if those numbers are far off, that may be an issue with the index, or it may be an issue with the analyzed data, and reanalyzing your database may actually help, right? So it expected 17,380, and it found 17,280, 17,330 and 17,280. That's actually fairly good. It was just 50 off in the 5-figure number, right? That's cool. And it took 3 seconds, 3 milliseconds. That's not bad, right? The problem is if we increase the number of records. I'm not going to do that because just inserting the data will take forever. But what we see is we have a single table. So imagine that table grows over time because we're adding and keep adding new measurements. So what we want to do is we want to be a little bit more, we want to be a little bit more fancy in the way we do stuff. And we drop the current table just so we have a clean start. And we do the same thing. We create the measurement table. And what we do then is we create so-called descendant tables, right? So those are tables that inherit the data schema from the table that they inherit from. So we have that, and then we say, hey, month 1 would be June, month 2 would be July, month 3 would be August, right? Super simple. So we create those. The only thing is, every time we add a new month, we need to remember that we add it at the new inherent table, the new descendant table. And then it gets a little bit more complicated because we're looking at the old way, right? So now we need to use like a before trigger to tell the database, hey, every time I want to insert something. Oh, the interesting thing is from I see those 3 tables, but the data would be available from the inherited table from the root table. So, but for inserting, I need to capture this event, like, hey, somebody wants to insert something into the database, and I need to look at the timestamps and say, hey, so that timestamp is equal or larger than June 1st, but it's less than July 1st. So I really want to insert that into the June database or the June table. Second thing, from July 1st to August, up until August 1st, I want to add it to the July table. And then onwards, I want to add it to the August table. The interesting thing is we really need that. So we need to limit the range until September 1st, because otherwise we would keep adding data to the August table in case we forgot to add another table. So what we really want to do, if we add data which is not in the range of any of those 3 tables that we want, right? We have monthly tables. We want to raise an exception, and that basically gives you like, hey, sorry, but the time range is outside of the acceptable ranges, so we don't care about that. So we need to create the trigger. It doesn't really matter if you're not like super familiar with Postgres or PLSQL. Just imagine it to be Java. It's basically the same thing. The only thing is, so as I said, we create a before trigger. That means we tell the database every time before you actually execute the insert, please call that function, right? And we say we want to execute that on every single row. So even if we do batch operations with like 10 or 100 rows, we want to make sure that we execute that for every row, just because in a batch of 100 rows, you may have actually data for June, for July, and for August. So we want to make sure that we add those to the same, to the correct tables. So we attach this trigger, and if we look here and we give data grid a second to update. By the way, thank you for JetBrains. Data grid is an incredible tool. There we go. There is the trigger, and now the database will execute that every single time. We just created the index afterwards for the last example, but let's do it here. The interesting thing is we really have to create those indexes on the inherited table, on the descendant table. That's one of the things we have to do in this example. And remember, if you need another month, if you need September, you need to create an additional inherited table. You need to create the index, and you need to remember to update the trigger function to make sure that you're now adding the new data into the August database. Same thing, we're adding values into our database. As I said last time, don't look at the numbers, especially like the execution time. It does not really matter. It probably takes a little bit longer. The trigger version is really not very efficient, but it worked and it was the way forward in the past. There you go. And as I said, I can open up the database as the database. I keep saying database, the table, and it does not matter. So we're June 1st. If I order the other way around, we're August 31st. So the data is all available from the measurements table, but the actual data is in the monthly chunks, right? So we have June 1st to June, what is it? 30th, probably 31st. I think it's June 30th, right? Same thing. It's July 1st and July 31st. And the last one is August. So nothing fancy here. If we look at the execution, we see that now it is much, much larger. And the interesting thing is how this thing happens. So the database decided we have a we have 3 descendant tables, and we have a table they inherit from. So the actual parent table, the root table, is here, and the database thought maybe, just maybe, there could be data in the parent table, because that is possible, right? Just because we inherit from a table does not mean that the parent or the root table could not contain data. So it decided, well, I probably have to do a sequential scan because there is no index on it. But it did not find any rows. There you go. It did not find any rows. It did a single loop. It did not take any time at all, right? And then for the 3 inherited table, for the 3 descendant tables, it decided, hey, cool. I have the index, so I can just execute the index on all of those. The horrible thing, you remember, we just asked for like 2 days. So in the old version, the database was not able to understand what data chunk may actually contain that kind of information. So it just decided, hey, I probably have to look at all those like partition tables, descendant tables. And we see there was basically nothing happening. There was no outcome of any of those. 0, 0, and here's our 17,280, right? So it looked for all of them. Still, the index lookups are extremely fast if there is no outcome of the index. Remember, the indexes are super small because they're per chunk or per partition. Good thing, but not perfect. So the next step, and that is where Postgres is these days. Let's remove all this stuff again. And we actually use drop table cascade, which means, hey, please throw away everything that somehow belongs to the measurements table, and that includes all the descendant tables. So that way I just deleted all of them, including all the partition tables. So let's go ahead and do the same thing, except for this time we say, hey, by the way, when you create this table, what we really want is we want them to be partitioned by range, right? We talked about the range, and we say the column that matters for the range is the timestamp. So we're creating time ranges somehow, right? And then we have a slightly different syntax. Here we say we want to create a table, and we still call it month 1. It could be June, July, and August. And we say this time we don't inherit from the root table, but what we say is what this table is, it is a partition of measurements. And it automatically understands, oh, okay, cool. So that means I'm a range partition. And as a range partition, I'm valid from the range of, because we have a timestamp, right? So we have a timestamp with time zone. So it understands from the 1st of June to the onwards to 1st of July, that is my valid range. And we do the same thing. And the cool thing, So we execute that. And same thing as with the last example. Every time we need a new month, we need to remember that we need to add a partition. But what we need to do is we do not need to update any kind of weird trigger or anything. And the other cool thing is that this time the index is actually created on the root table, and all of the partition tables will automatically inherit or gather this index. So every time a new month comes forward, we just need to add a new partition, and we need to define a range, and we're good. And that could be something like a nightly job, super simple stuff, right? On the 30th or 31st, or even on the 20th of a month, you're just going to already create like the partition for the next month, just in case somebody needs to add data a few days in the future, like an invoice date or anything like that, right? And invoice date may be even 30 days in the future or something. We're going to add our data again, simple stuff. And there's two things. You remember the partition pruning, where the database has the option to understand, do I need tables or partitions, or do I not need them? Let's put partition prune off. So that's a property in the database, in this case for the session, and we said, please don't do any partition pruning. So if we execute the query again, this time against the new database, first of all, we see this time it understands there can be no data in the root table, which is good, right? So one thing, there's no sequential scan on the root table this time. But it still has to do the index scan on all of the three partitions, because what we said is we don't want partition pruning. There we go. We don't want partition pruning. It's a little bit too small. And then we have 0 rows, and 17 to 80. So let's turn partition pruning on and rerun this. And this time, the database does exactly what we expect it to do. It understands the range, and it understands, hey, cool, I only need to look at a single index, and that's good. Obviously, the execution time and stuff with the low number of partitions doesn't really make a difference. So that works pretty well. And now is the interesting thing. What can timescale bring to the table? And I need to speed up just so slightly. I have about 3 minutes left, which is great. That works for me. So we want a data table again. I just deleted the previous data. Oops. I just created the previous data. I'm creating the table again. And here is some timescale magic, right? So I'm saying the database, hey, I have the measurements table, and I have the timestamp column TS, and please create a hypertable. That's our definition or our term for a time series table in Postgres or in TimescaleDB with an interval of 1 month. So that does the same thing, except for we just say, hey, we want 1 month chunks. We don't care how you create those. That's what we want. We add the index data, we insert the data again. And I can even go ahead just to make sure while this is inserting, make sure that partition pruning is off. We don't really care for partition pruning because timescale hooks itself into the query planner and does the query planning itself. So we don't care for this property partition pruning on or off, which is great. And we actually existed before that. So we do the same query. Remember, I just disabled partition pruning. You see, we only look at a single partition. You see the name is slightly different. So for us, it's timescaleDB internal. That's and kind of unknown. We not really hidden different schema, but that's how we store and where we store all the information. And then we have our chunk, which is our partition, and that has 17,280 elements. And if we look here, what we see is we only see a single table. That's what we try to do, right? It's a fancy version of a view. If you actually want to see all the data chunks, you can do that. There is the timescaleDB internal schema, and if we look at that, and we give data grid a second to update the schema information, we can see that here's our chunk tables, right? Okay, so, but that would be boring, right? So why would I use timescale, right? Because the beauty is in a different thing. So what we can do, and we just recreate this table, right? What we can now say is, hey, I don't want monthly chunks. I really want daily chunks. And I just do that, right? So I recreated the table, and you can actually change the chunk interval after the table is already created. It will not change previous partitions, but if data keeps growing over time and you collect more data in the same time, you can change the chunk interval. And I do the same thing. The only thing I changed here is to say, hey, I actually want daily chunks now. So if I execute that, we're adding daily chunks, and when that is done, we execute the query, including the explain, and we see it now has to do a little bit more. It does a bitmap heap index, a bitmap heat scan now, but still with an index, and we're asking for 2 days. So what it does, it looks exactly at those 2-day chunks, right? So that's the beauty. And if we just quickly change or update the tables in the internal schema, what we see is that we get like a lot of more chunks. Basically, one chunk, I think it's around 90 chunks, 92 chunks, something like that, right? 94, so it's 92 chunks plus 2 internal other tables. And that's how easy it is when you want to do those kinds of things with timescale. With that, we are basically out of time. So where to go next? If you are into time series and you're interested to learn more about that kind of stuff, or if you know you need time series, we have a really amazing blog post about that. The next couple of days, there will actually be a blog post about how to lay out your table design if you need more metrics, different metrics. There's a couple of ways on how to lay out this kind of stuff, not only in timescale, but in general in time series databases. So that will be out. If you love NHL and love looking at data and trying to analyze those kind of stuff, one of my colleagues, she actually created this amazing data set for NFL games. She's big into NFL. I'm not, but it is really fun to play around with that. And the one of the most common use cases for time series is forecasting or prediction or any kind of analytics. So the forecasting stuff may be interesting to you. I'm pretty sure the slides will be changed, will be shared afterwards. And with that, I think thank you very much. And we're gonna drop over to the questions, I guess.
Hi, Chris. There are no questions now. Just to say, amazing talk, really interesting things regarding Postgres. Actually, I also work with Postgres, but haven't seen this kind of ways to, I don't want to say optimize the way we store the data, but yeah, really interesting techniques just when dealing with big information, not with a lot of information. And I saw that we were. Go.
Yep, sorry. The interesting thing is that is not only time series. So the partition stuff is interesting when you have a lot of different customers, customer data, invoices, all the kind of stuff. Whereas invoices is some kind of time series. So basically anything that grows has most of the time has some relation to time series. So yes, I agree. The partition thing, I think, came in with Postgres 13 or 14. I'm not 100% sure. It's not like super old yet. But yeah, super interesting stuff.
Awesome, Chris. So that was my comment regarding this. Thank you so much for the talk, and hope to see you here. You're invited to come at any given time.
Absolutely. Yeah. Thank you for having me. It was a pleasure being around.
Thank you, Chris. Un anuncio para Bye. Un anuncio, no se olviden de registrarse en el Meetup y por favor hacer sus preguntas para el sorteo de las licencias de IntelliJ que se van a hacer al final del evento. Thank you, Chris, again, and gracias a todos. Nos vemos.